If you've been running around this circle for long enough, you're familiar with this drawing. For those of you who are not familiar with the OTC-X1, in 1960, Otis T. Carr had Ralph Ring and two other people operate what he refers to as a circular foil craft, and that was in Apple Valley, California. And it teleported downrange 10 miles and back, and there's a whole story behind that. You can check out some interviews with Ralph about his whole story there, but bottom line is, they tested this craft, they got it to work, there were witnesses, the FBI came in, raided the facilities, confiscated the craft they were working on, all the materials, and completely disbanded OTC Enterprises. Today we have pods located around the world who are working on basically reverse engineering this thing from what remains from OTC Carr's amusement device patent and his toy kit plans, and another item called Dimensions of Mystery, which is a poem that encodes all the secrets of how this thing is supposed to work. Now you're caught up. So the purpose of this video today is to discuss the wiring test that was performed down in Australia a few weeks ago. It's been some time since I posted that introductory video because there's a lot of other things that have been happening, and I've been trying to stay on top of that. We had a new pod join us with a couple of engineers, and I've been going back and forth with them for days. Anyhow, so there's two things I'm going to talk about today. One is going to be the wiring on the capacitor plate and how that affects rotation and counter-rotation on this craft. The second item I'm going to address are the tests that are being done that are right now inconclusive but seem promising. They're coming out of this new engineering team in the United States. Okay, so to catch you up, right here in the middle, this is a side cutaway view of the OTC-X1 prototype craft. In the middle you have what's called an accumulator, the central accumulator, and according to Carr, this thing is supposed to receive energy from the ethers or some such thing, and basically just look at this as a battery. So we haven't figured out how to do that yet, but we do have batteries, and we've been able to test with that with known electrical principles. So we're going to call that the battery. The blue line coming across here is the edge of the disc. So here's a little filter I have for my light kit. Just turned on edge, and this thing, it rotates. Okay, imagine a pencil in the middle and it's spinning. You got a little top here. Mounted to this disc, this blue plate, it's segmented. There are actually 12 segments. 6 of them have aluminum capacitor plates, and they're U-shaped and they affix to the edge of the disc. So if you take a look at the disc from the top, you have aluminum, non-aluminum, aluminum, non-aluminum, all the way around, cut into basically a loose pie. So you have alternating materials of conductive and non-conductive surfaces. So that's what this red line here represents, is a 9mm thick capacitor plate that is affixed to the rotating disc. It's fastened to the disc simply by one nylon bolt. So every capacitor plate in the prototype that's been constructed down in Australia uses one bolt to keep it on there. All right. This blue piece on the top and this blue piece on the bottom are called trunnions. Each of these trunnions hold in place what Otis T. Carr referred to as a Utron. A Utron is a rhombus-shaped solid. Imagine two equal cones touching each other. If you look at this rhombus from the side, it looks perfectly square. If you look at this Utron from the top, it looks perfectly round. So geometry plays. All right, so we've got this aluminum Utron that's mounted to these trunnions, which basically they just sit there. There's nothing turning them, they're just there. I talked to Ralph Ring about that. He goes, they don't spin, they just sit there to freewheel. All right, so now you get kind of an idea of the motion. So that's one of the two moving parts that Carr talked about. One is the plate. The other moving part is the outer hull. So if you imagine the plates moving, let's say, or the inner disc is that whole disc assembly with all the Utrons and plates attached to it, turning on the spindle in the middle, let's say it's moving in a clockwise motion. The idea is to get counter-rotation going, and that's what the outer hull is. So these black lines here are the outer hull, are affixed, let's say, the spindle at the top and the bottom. On the inside of the hull, attached to the superstructure, is a C-shaped electromagnet. Okay. These blue dots simply represent how they're affixed to the superstructure on the inside. And once again, nylon bolts are done to hold those in place. The electromagnet is comprised of slices of iron. I forget how many he told me, but we can figure out the details later. Let's say it's 24. Okay, whatever it is. So they're about that thick. You know, they're affixed to the inside, bolted together, and he's created these what he calls formers, and they're just used to hold the enamel-coated magnetic wire in place. And if you recall back to your grade school, we've all created magnets using a wire and a battery and a nail. That's basically what we're doing here, is you're sending current through a coil wrapped around this ferrous material to create an electromagnetic field, all right, or magnetic field, I should say. You're creating magnetic flux. So one thing that he shared with me a few days ago about this, I'm going to give you some details. Around this former, he just started wrapping the wire. And like I said, he's using a 30 gauge enamel-coated magnetic wire. And he starts on one side and he goes to the other. And if you've ever been fishing, you see that reel, you know, sending the fishing line out. It goes from side to side. That's how you wind your electromagnet. So you go up one, down two, and you just repeat this. And the number of times that he did it for his prototype was 13. He went up and down 13 times. You may decide to use a different gauge wire. You may decide to do it more or less times. That's up to you. I will comment that when it comes to making electromagnets, the best kind of wire that you can use is a flat wire. And the reason for that is if you take a look at a wire on end. Okay, so this is our wire, right? Current is flowing this way into the board. Accompanying every electric charge is the magnetic field that goes out at what, 90 degrees. So you have these radials of magnetism, right, that go out 306 degrees around the wire. Now, because of the angles here, if you're wrapping it around, creating an electromagnet, you may not be able to get the most efficient amount of field into your iron core. So if you use a flat wire, you're going to have more energy going into your electromagnet than you would with a wire. So anyway, that's my 2 cents on electromagnetism. Simply Google electromagnet, and I promise you will find that same information out there. Anyhow, so that's my contribution. All right, so we talked about the C magnets, how they were made. We talked about the U-shaped capacitor plate. Now, I know a lot of you out there who know something about electronics will go, golly, isn't a capacitor 2 plates? Should these even be connected? Well, all I have to say about that is yes and no. It just depends on what you're trying to accomplish. And in this case, what Carr was trying to accomplish was rotation. What we're not considering is how the rotation was accomplished. He's not using AC current. Maybe he's not looking to place a charge in a dielectric material. There is the Forbes homopolar dynamo. With the homopolar dynamo, you have a battery, you have a copper plate and a magnet, right? Like this, not an electromagnet. He had a permanent magnet, I think. And he applied a charge to the inside of the plate, went into the battery here, the other end of the battery there, and that plate would turn in one direction. You know, even that kind of stuff. Tesla. Take a look at his notes on Forbes homopolar dynamo, and that will reveal to you how this craft is likely supposed to be wired. So I'm going to show you how they did it down under, and how they did it in Australia, okay? So really what he did, if you've seen my previous videos, you've seen the cutaway version of the prototype craft that he built. It's really cool looking. He says it's pretty darn solid too. In fact, he said he stuck this thing like on a router motor or something just to spin the disc, and I asked him, dude, are you like standing next to it when you did that? Because he was just using nylon bolts. And like I said, there's 12 of these iron electromagnets spinning around on the outside. I don't know if that part was spinning, but regardless, those capacitor plates are 9 millimeters thick, and there's 6 of them, and they're pretty heavy as it is. He said the whole thing stayed in place, so it was pretty solid. Anyhow, he has a lot of confidence in the design, and I guess you should be too. Anyhow, where was I going with this? We were talking about how this thing was wired. So what he did was he took his model apart and he just yanked out one of these C-shaped electromagnets, and he yanked out one of those U-shaped capacitor plates. That's not really a capacitor in the practical sense of the word. And what he did is he ran a battery. Let's say this is our battery here. All right, let's say this is the positive lead, and over here we've got our negative. All right. So what he did was he connected the positive lead, right? So positive lead came down here, and he split it off. He had one connect to one open side of the U-shaped capacitor plate, and the other to the other side. For the negative lead, he came off this way, and he stuck a switch in here. All right, he wanted to control this thing, right? And he put a contact here, so he can control this, right? So that would close the circuit on that battery. Now he needed to charge the electromagnet, and basically he took a separate battery to do that. So he, here's our DC source here, right? And he just had that energized. So now it converted this to an electromagnet. So with the, darn it. All right, I'm back. With this C-shaped magnet energized, he held it in one hand, I guess, and he just simply dangled the U-shaped capacitor plate in front of, right near the opening of the magnet, and he closed the circuit by throwing the switch. And that plate just moved right through the opening of that C-shaped magnet. Now we have energy. We have a means of applying force to cause rotation in the central rotating disc assembly. Now keep in mind, on the face of this disc, there are 6 of these plates. So with aluminum passing through a magnetic field, it causes another force of motion. This is Lenz's law. So we're simply applying science that we already know about, just to get the rotation going. Also on this disc, in between the capacitor plates, you have mounted a Utron. I think I described what a Utron is. A Utron is it's round and square at the same time. So if you view it from the top, the Utron is perfectly round. When you view it from the side, it's perfectly square. And it's basically a solid that's comprised of 2 opposing cones. And this is a solid piece of T6 aircraft aluminum. It's like 2011 composite. The composite for the aluminum in the Utron, I'll have to post that later. I forget what it is, but regardless, it's aircraft aluminum. So in between the aluminum plates, you've also got these Utrons passing through the C-shaped electromagnets. There's 12 of these all the way around the periphery of this thing. So you've always got aluminum passing through, be it a Utron or a capacitor plate, Utron, capacitor plate, applying that force, allowing this thing to spin. Now, Walter, you've got a manual switch here. How do we control on, off, and closing the circuit on the capacitor plates? Well, what he's planning on doing is he's attaching what Tesla referred to as like a sliding contact. So if you can imagine just a piece of copper, and his is going to be spring loaded, and he's going to position it right here. Okay, the next thing I want to talk to you about is a Utron test that has been recently revived. If you recall from my previous videos here, you can go check it out right here. It's the Utron spinning in a Dremel test. And basically what was done in Australia was they connected a solid Utron, a solid aluminum Utron, to a Dremel. And for those of you who don't know what a Utron is, it's basically two opposing cones like this, and it's solid aluminum. On the side it looks perfectly square, from the top it looks perfectly round. This was an invention of Otis T. Carr, and it's part of the OTC-X1 craft. Anyhow, so the theory is that this is an accumulator and you should be able to get power out of it, and this was tested. So they wanted to see if they could generate a magnetic field by spinning it. They put it into a Dremel. They spun it up 32,000 RPMs. They held a permanent magnet, in this case a neodymium magnet. In the last week they just stuck it in a little plastic spray paint can lid and held it right next to the spinning Utron, and it spun like crazy. They put a meter on it. Okay, and they were pretty excited because here's what they found out. At the highest setting, with the meter set at 1,000 volts, what it was like, it was infinite. They couldn't even read it. So they changed gears. And they said, all right, well, let's do a reading at AC. So they set it to AC, and what they found was that the unit was producing some of the neighborhood of about 15 volts alternating current. Wow, that's amazing. An infinite amount of direct current, about 15 volts of alternating current. What causes this? Why, when we chuck a solid piece of aluminum into a Dremel motor, does it create this kind of power? Well, let's think about that. The material is aluminum. Aluminum is paramagnetic. That means that when aluminum enters a magnetic field, it becomes magnetic itself. When it exits a magnetic field, it is no longer magnetic. So it's possible that this piece of aluminum is inheriting the magnetic field from the spinning motor. So, okay, interesting experiment. Interesting, somewhat promising results. Let's do some more testing. So they still think that by spinning the Utron they can get some power out of it, which is fine, and I'd love to see that. So I suggested they take the Utron out and take this magnet and hold it next to the Dremel without this thing chucked. They had it right next to it. I mean, there was nothing. I mean, that magnet would not spin, it wouldn't budge, it wasn't doing a thing. Curious, so why would that be? Well, it's possible that within the motor itself, maybe there's some new metal foil that's blocking any kind of magnetic fields that are coming out of it rather than being inherited through the shaft. All right, so what else can we do to test this? I suggested that they completely separate the Utron from the turning motor and try again. Well, their interpretation of that was to go out and purchase an extension. It's a 3-foot extension that Dremel, it's a flexible cord that you can attach to the Dremel, and they were able to get the Utron 3 feet away from the motor. They reconducted this test. They found that the magnet spun. Well, that's pretty interesting. Why is that? Well, it's still physically connected to the motor. We don't know what the core is comprised of within this extension. It could be ferrous. It could be transferring that magnetic energy into the aluminum Utron. We need to get it separate and apart. So when I talked to them this morning, we've been exchanging emails, I suggested they do this by using some form of apparatus that utilizes nylon bushings, chain sprockets, non-conductive, non-ferrous material, and get it a distance away from the motor and try again. So let's say they do this. In fact, they're setting that up right now. I don't know how they're going to arrange it. They didn't say specifically how they were going to do it, but they're coming up with something to get it away. What do you think? Do you think that when they separate this Utron from that field and they come back and they set this magnet right next to it, do you think that it'll spin or not spin? I'd like to see your comments, and thanks again for watching.